Welcome to the online lecture for electromagnetics ELE531. The way of expressing a complex quantity or a phasor in frequency domain will be discussed today. A quantity having a magnitude and a phase angle is called a phasor. In most electrical circuits, the frequency of a source or input signal does not change. Rather, the amplitude and or the phase angle change. Therefore, we can skip the signal frequency while solving such electrical circuit problems. Frequency domain representation of a time harmonic signal gives a hint on that. In this lecture, we will learn how to express a time domain electric or magnetic field equation into frequency domain form and vice versa. After watching this video, you will learn how to derive the Maxwell equations in frequency domain from the time domain form. Time domain is the analysis of mathematical function, physical signals with respect to time. In the time domain, the signal or function value is known for all real numbers. For the case of continuous time or at various separate instances in the case of discrete time. An oscilloscope is a tool commonly used to visualize real-world signals in time domain. A time domain graph shows how a signal changes with time. Look at the graphical representation and mathematical expression for time harmonic signals in the time domain. Here, omega is the frequency of the wave. A time domain expression includes the amplitude, frequency, phase angle of a signal or a function. We usually use cosine function for representing a time harmonic wave. In some cases, we might use sine function for a time harmonic function. In electrical engineering, the frequency domain refers to the analysis of mathematical functions or signals with respect to frequency. A frequency domain graph shows how much of the signal lies within each given frequency band over a range of frequencies. Also include information on the phase shift must be applied to each sinusoid in order to be able to recombine the frequency components to recover the original time signals. Fourier transform converts a time function into a sum or integral of sine waves of different frequencies, each of which represent a frequency component. The inverse Fourier transform converts the frequency domain function back to the time domain function. A spectrum analyzer is a tool commonly used to visualize electronic signals in the frequency domain. Let us find the composite signal shown in the figure. Here the signal is presented in time domain, which is also transformed into a series of signals of different frequency named a Fourier series. The frequency of any of these constituent signals is an integer multiple of the fundamental frequency. Fundamental frequency is the lowest frequency in a Fourier series. In this course, we will discuss only a simple sinusoidal wave that can be expressed with a sine or cosine function. In frequency domain, a sine or cosine function is expressed with its amplitude and phase angle. Look at the mathematical expression of the function y with amplitude a0 and phase angle phi. Euler's formula is a mathematical formula in complex analysis that establishes the fundamental relationship between the trigonometric function and the complex exponential function. Let us consider a function y in time domain is a naught e to the power j omega t plus phi in the phasor form. So yt, we can use a Euler formula to decompose the phasor form, equal to a naught cosine omega t plus phi plus j sine omega t plus phi. So the cosine function is the real part of yt, the phasor form. So you can write yt equal to a naught cosine omega t plus phi. That's the real part of the Euler's formula. So now a naught cosine omega t plus phi is the real part of this. So we can write it like real part a to the power e j omega t times e j omega phi. Now we separate e to the power j omega t, and if you remove e to the power j omega t from the expression, we'll come up with a to the power as w is equal to a naught e to the power j omega phi. Here ASW is the frequency domain component that has the magnitude a naught and the phase angle e to the power phi t, and this format is called the frequency domain format. Similarly, we can write an electric field expression ET equal to E naught cosine omega t plus theta AX. So now it can be written using the phasor form. So we can write real of e to the power real E0 e to the power j omega t plus theta AX. Now we can separate e to the power j omega t and eventually drop it from the expression. Then we come up with the frequency domain form. So that is equal to ES, that is ES equal to E naught e to the power j theta AX. Similarly, we can do for magnetic field expression HT, that is in terms of sine omega t. So we convert it to cosine first. So we write cosine omega t plus theta minus pi over 2. So we always convert sine function to cosine function by adding a negative pi over 2 phase angle with that, and then we replace it. So we come up with j real hs e to the power j omega t. So finally the frequency domain form will be hs equal to negative j h naught e to the power j theta az in the frequency domain. Assume a function named a. In frequency domain, we call it as. In this course, the suffix s is used for representing a function in frequency domain. The respective time domain function is a. We may write a frequency domain parameter as a function of omega and its time domain form as a function of t. To convert a frequency domain function to its time domain form, we should include e to the power j omega t with the phasor form of the function. For instance, a frequency domain function as is equal to ao e to the power j phi should be multiplied with e to the power j omega t. Then we simplify to ao e to the power j omega t plus phi. Finally, we take real part of the function to derive the time domain form of the given function, and it becomes a to the power cosine of omega t plus phi. In example 1, the frequency domain function as with magnitude 10 and phase angle phi over 4 can be written as a function of t is equal to 10 cosine of omega t plus pi over 4. If a function has a factor negative j with magnitude, we can replace that with a phase angle of negative 90 degree, or represent that with a sine function as shown in example 2. To explain this, let us consider e to the power of negative j pi over 2 is equal to cosine pi over 2 minus sine pi over 2. That is equal to 0 minus j. Finally, minus j is equal to e to the power of negative j pi over 2. Also, see the following two-dimensional diagram. The cosine function or a real component of a complex number is placed in x-axis, and a negative sine function or imaginary part in the vertical axis. The phase difference starting from real axis to the imaginary axis is 90 degrees. Translate the real axis and the imaginary axis to get the negative cosine and positive sine function. The clockwise shifting indicates a positive phase angle. The clockwise shifting indicates a negative phase angle, and the counterclockwise shifting indicates a positive phase angle. We place the function on this system. It will be pi over 3 equal to 60 degrees shifted in counterclockwise direction from the negative j or sine axis. So we write the equivalent time domain function is 5 sine of omega t plus pi over 3, or from the cosine axis, the function will be 5 cosine of omega t minus pi over 6. The sine of the phase angle is minus because the function is shifted in the clockwise direction from the cosine axis. The derivative and integral for a sine and cosine function is also a sinusoid. For example, the derivative of a sine function is a cosine function. Refer to the diagram shown before. It is evident that a cosine function is just a sine function with a phase shift. Therefore, we can easily replace such derivative and integral operators in frequency domain. Look at the mathematical workflow for obtaining the frequency domain equivalent j omega for the derivative d over dt. Similarly, 1 over j omega is the frequency domain equivalent for the integral of a sinusoid. We are going to transform the time domain Maxwell's equation to the frequency domain now. We consider one of the Maxwell's equation. Curl of E field is equal to negative partial time derivatives of B field. Replace E and B with the real part of their corresponding uh, replace E and B with the real part of their respective Euler's expression and derivative with j omega. Then drop the similar factors from both sides. We get curl of E s is equal to the negative j omega of Bs. The suffix s is to represent a frequency domain variable. Likewise, you can get the other Maxwell's equations. You might need to know all of these Maxwell's equations, practice them a lot so that you can recall them anytime you are asked for, without winking on the lecture notes or aiding of the textbooks or surfing on the internet.